Hi everybody. Today we're going to start talking about forces. If you remember when we started talking about motion, I said that we were only going to initially look at the way objects actually change their motion, how they change their velocity, they speed up, they slow down, they change their direction. We weren't going to look at the causes as to why they changed that motion. Now we're going to start looking at those forces that can affect motion and are essentially the causes of why objects change the way they move. So our objectives for this lesson are to define force and net force, to determine how net forces can cause changes in motion, and finally to classify the types of forces that we're going to use in the classroom based on their cause. So hopefully you know the simple definition of a force. It's a push or a pull. But in physics we have a little bit more meaning to a force. We say a force is defined as any action that can change the state of motion of an object. So it may be a push or a pull, but when we look at it, we also want to look a little deeper into it and see what that push or pull can do when it's exerted on an object. And what is meant by a change in the state of motion of an object? Well, that means it's changing the way it's moving. It's changing its velocity. And a change in velocity is acceleration. So if an object accelerates, it's changing its velocity, and therefore it's changing its motion. So essentially, when we look back and we say a force, a push or a pull, that essentially can cause an acceleration of an object. Now we have to start looking at whether or not we know whether or not a force will change the motion of an object, or will it accelerate it. And we have to start looking at a net force. There's a force exerted on all of us every day. We've already discussed that. Gravity. And we're not all moving. We're not all falling towards the center of the earth every day. So as a result, we have to look at why, if a force is exerted on an object, why doesn't it change its motion? And that's because we don't just look at every individual force that's exerted on an object, but essentially we look at what's called the net force, or the sum of all the forces acting on the object at a particular instant in time, to determine if the object will then change its motion. Now when we look at net force, we have to remember that along with displacement, velocity, acceleration, force is going to be a vector for us. It's very important that we look at not only the size, the magnitude of the force, but we also look at the direction of the force. So when we're determining the net force, we have to consider both the size, how big the force is, and in what direction the force is exerted. So let's take a look at this pair trying to move this couch. You can see that they're both pushing with an equal amount of force onto the couch. And we can tell that by those arrows. Remember, we can still represent vectors with arrows. So it's telling us that the magnitude of the force that they are both exerting on the couch is the same. What's different about it, though, it's in opposite directions. The girl is pushing to the right, the guy is pushing to the left. So when that happens, when you push it the same amount, but they're in opposite direction, those forces are balanced. It essentially means that all the forces are equal in magnitude in opposite direction, and as a result, the net force on the object is zero. They all cancel each other out, essentially. The object, as a result, will not change its motion or accelerate because the net force acting on it is zero. You're only going to have a change of motion if the net force is not zero. We're going to use another word in class 2, and it's called equilibrium. If the forces exerted on an object are balanced, the object is said to be in equilibrium, and that means the object will not change its motion. So if you hear that word as we talk in class, equilibrium, it just means that all the forces in all directions are balanced. They're essentially equal and opposite. All right, now here's a sticky point for most students. If the motion does not change, it means acceleration is zero. But that does not necessarily mean that the object is not moving. And we've talked about this in class when we've even talked about an object just moving at constant velocity. Acceleration would be 0, but that does not mean that the object cannot be in motion. It may be at rest, but it also can be at motion, just moving at constant velocity. So please do not think that 0 acceleration means that an object is not moving. It just means it's not changing its velocity. So the object either has to be at rest or moving with constant velocity. In this case, of course, if you look at that sofa is staying still. But if an object was already moving, there are forces perhaps being exerted on it. If all those forces are balanced, it's just going to continue to move in the way it is currently moving. Okay, so if you've gone through your graphic organizer, you should have filled in the left column where it asks questions about whether or not the forces are balanced. Your answer should going toward the yes side on the left-hand column. Does the net force cause a change in motion? No. Does acceleration exist? No. And what type of motion exists? Constant motion. Okay, now we're going to continue, but now we're going to look at the right-hand side of the column of your graphic organizer, where it tells us the forces are not balanced. So forces exerted on an object are unbalanced. That means there will be a net force. The object will change its acceleration and change its motion, and the acceleration always occurs in the direction of the net force. So if you look here, now as a result, we have our two people trying to move the sofa. They're both on one side of the sofa. They're both pushing in the same direction. So the net force is essentially the sum of both of their forces. And we find that the sofa now accelerates. And which direction does it accelerate in? It accelerates in the direction of the net force. Just remember that acceleration is a change in velocity. So a net force just can cause a couple different things. The net force can cause a change in speed. It can make something change the way it's moving as far as how fast it's moving. It can cause simply a change of direction, which is when we talked about gravity. When an object goes up in the air and it comes back down again, at that instant, at its peak, gravity did not go away. That force exerted on the object by gravity did not go away, but what simply happened is it changed the direction of the motion of the object from going upwards to going downwards. Or it can also do both. It can change both the speed and the direction. All right, so now if you've figured out all the factors you have to fill in for your right-hand side of your graphic organizer, where the forces are not balanced, does the net force cause a change in motion? Yes. Does acceleration exist? Yes. In which direction? In the direction of the force, the net force. What does the acceleration do? It can change the speed, it can change the direction, or it can change the speed and the direction. Okay, now we're going to flip over to the back side of your graphic organizer, and that's just to give you an idea of the types of forces that we're going to talk about in class, how we will represent them with variables, and what type of information you need to know about them. Okay, so we start off with the two types of forces that we're going to talk about in class. Forces can either act on an object through contact or at a distance. Contact forces result from physical contact between two objects, meaning they actually have to touch. The type of contact forces we'll talk about include applied forces, something that you do when you push on something, a normal force, a friction force, tension, and a spring force. So these should be the 5 blocks underneath contact forces on the left-hand side of your graphic organizer that you should fill out. Field forces are those forces that do not involve physical contact and they act at a distance. They don't actually need to touch the object in order to exert a force on the object. These are forces such as gravity. Gravity doesn't reach out and touch us. The surface of the earth doesn't need to reach out and touch us. That force exists. It's a field around the earth that exerts a force. There are 2 other field forces that we will work with later in the year. One is the electrical force and one is the magnetic force. Okay, I'm going to go through and I'm going to describe each of the forces, and I'm going to give you the variable that we're going to use to represent them in class. Because you might see, looking at this screen, that force is represented with an uppercase F. So we need to be able to differentiate it. So we're going to be using some subscripts again. So what's an applied force? An applied force is a force that's exerted on an object by a person or another object. There's actually something doing some pushing or pulling. We're going to represent that with an uppercase F, and I'm going to use the subscript APP just to know it's applied. It's not one of the other forces that we're going to talk about. The normal force is a support force exerted upon an object which is in contact with another stable object. This means something is supporting it. So if you have you standing up here in class on the floor, the reason that gravity doesn't pull you towards the ground and change your motion is because the floor is supporting you. That's that stable object providing another force. It's supporting us. Or if you think about a book sitting on a table, again, gravity is exerting a force on that, trying to pull it down to the surface of the earth, but the table surface is providing a support force that prevents the book from moving under the force of gravity. It's called the normal force because it's always perpendicular to the surface that is exerting the force. So if you remember from geometry, that word normal means perpendicular. And it's going to be represented by an F with the subscript N. Friction. Friction is a force that's exerted on an object as it moves or tries to be moved across a surface. And we kind of know what friction is. We experience it every day in our lives. There are two types of friction that we're going to talk about in class. Kinetic, which means when an object's in motion, and static, which means when an object is not in motion. The force of friction, you always have to remember, always opposes the direction of motion. So when we're looking at an object that has a net force exerted on it, and it's actually moving or trying to move in a certain direction, friction is always going to be in the opposite direction of that motion. Friction is going to be represented by a lowercase f as the subscript. Tension. Tension is a force that's transmitted through some type of string or rope or wire when it's pulled tight. Right? Usually a tension force is exerted somewhere in things that we'll talk about in class where we're hanging something. The tension force is directed along the length of the wire, and it pulls equally on the objects on the opposite ends of the wire. So it's, if you think about it, it's just sort of a force that if you don't really imagine the wire exists, but there's again some type of support force or something that's holding it, and it's just provided by a wire. Tension is the only one that we don't represent with an uppercase F. You can use an uppercase F with a T as a subscript, but I'm going to use the convention of an uppercase T to represent any force that is a tension force. And our last contact force is called a spring force, or sometimes called an elastic force. This is the force that's exerted on an object when a spring or a rubber band or something like that that is kind of stretchy is compressed or stretched, and then an object is attached to it. Well, what happens is when you let the object go free and you let the stretchy object, be it a spring or a rubber band, try to go back to its equilibrium position, it will now exert a force on the object that's attached to it. So a spring force is something that we're not going to look at until a little later in the year, but you just want to know that it's one that we will address as the year goes through. And again, I'm going to denote it with an uppercase F, and I'm going to use SP as the subscript. You might find some people use elastic or something like that, but that's what I'm going to use just to be consistent. All right, so that sums up the contact forces that we're going to talk about. The last forces we're going to talk about are simply the field forces, or the forces that do not require contact. All right, the major one that we're going to talk about for the next couple of weeks is the gravitational force. That's the force due to gravity on which the Earth, the Moon, or any other massively large object attracts another object towards itself. Everything in the universe experiences a force of gravity with respect to other objects. When we're talking about objects though on the surface of the Earth, we know that that force of gravity is directed downward, and then we need to realize that there are certain things that are going to confuse us in class. The gravitational force itself is a vector quantity. It has a size, and it's always pulled downwards. Here's where we get a lot of confusion in this class. The size of that force is called weight. So when we start to talk about the weight of the object, we're talking about the size of the force of gravity that's exerted on an object. This is one where we start again, where we have a vector and a kind of a scalar quantity. This is one where we do have a different name for the size of. And unfortunately, it's a word that we use every day in our real lives, but that doesn't really make us think of a force. So you want to make sure that you understand what I'm talking about when I talk about weight. I'm talking about the size of the force of gravity exerted on an object. The last two field forces are going to be pretty brief because we're going to cover them in depth further in the year. So the first one is the electric force, and this is the force of attraction or repulsion that exists between electric charges. Think about static electricity when you build up a lot of static and something sticks to a sweater or something like that. That's a force that exists that holds that object or attracts one object to another. And then the magnetic force is a force that's created around a magnetic field. So if you have a magnet, it may attract things to it the closer something gets to it and make an object move towards the magnet. We're not going to talk about them much in the next couple of weeks, but we will address them later in the year. All right, so that covers your introduction to forces. You should have your graphic organizer for forces completely filled out. And if you have any questions, please make sure you come prepared to ask.